So another problem we have here, a centrifugal compressor so handles 300 cubic feet per minute of air at the pressure of 14.7 psi and at 80 degrees Fahrenheit. So the air is compressed to 30 psi, so from 14 to 30 psi. The initial speed, so that is during the suction, that will be 35 feet per second, and the final speed, which is on the discharge side, is 170 feet per second. So if the initial compression of the polytropic with N is 1.32, so what will be the work, okay, for the given problem? So let's first determine what will be the given the problem, no? So for the given, so usually we start with that one. So what will be the given of the problem? So we need to identify. So we have the volume flow rate, so that will be your B1. So we have your B1 prime, which is 300 cubic feet per minute. Then initially, so we have the suction pressure P1, which is your 14.7 psi, and it is now absolute pressure, so we don't have to add the 40.7 or for that one, so it is already absolute. Now for your P2 at point 2, so we have going to compress the air to 30 psi. So this is also an absolute reading also. Then our T1, which is initially, so we have 80 degrees Fahrenheit. So we're going to convert that one into an absolute. So we're going to add 460 in order to make it a Rankine. So that is equal to 440 Rankine. So take note, if thermodynamic processes or thermodynamic calculation, so it will always involve in the absolute pressures. So we'll be using absolute pressures and absolute temperatures. Okay. Then, so for T2, we have, so it's not given in the problem. There's no final temperature, so we have to solve that one. So not given in the problem. Then we have your N, so that is equal to 1.32. Okay. Then we have also the velocity 1, which is equal to 35 feet per second, and we have your velocity 2, so discharge, okay, discharge line, so that will be 170, so much faster than the suction side. Okay, so we have now the given, so let's try to do the solution. Okay, so first things first, we need to plot that one also in a curve, in a PV diagram, sorry, not a curve, but a PV diagram. So in order to have a good visualization of what is happening here, and also it will serve as a guide for us for the calculation. So I have here your pressure and your volume PV diagram. So initially, I'm going to draw the line here for our for the suction, no? Okay. So this will be your our point 1. So at this point, our point 1, then for our so our point 1, which is the pressure is P1, which is equal to 14.7 psi absolute. Now from there, it will be compressed polytropically. Okay, so I'm going to draw a polytropic curve here going up. Sorry about that one. I'm going to draw here. Okay, I'm gonna change this one to this color. So going up. So we have here your polytropic, which is your PBN raised to 1.32. So this curve. Now we have here your point 2 at this point. So that one. Then I'm gonna draw in here the line again to connect this one. So in the problem, it does not state if we have a clearance. No, so there is no clearance. So we assume the piston is moving at the top dead center. So during the suction and the compression stroke. So if we're going to draw the compressor here, so if we have the cylinder, so I have the cylinder dito. So I'm going to draw our piston of our compressor. Okay, so I'm gonna make it black. Then initially during suction stroke, and this is your compression stroke. So let's plot that one. Okay. So we need to erase this one. Okay, so we have here the schematic diagram. We have the PB dito. Then we have also the uh, piston arrangement, piston in a cylinder arrangement below. So indicating the suction and also the discharge stroke of the piston. Now we have your P1 at point 2 and we have also your P2. Okay, so that will be the final pressure which is being compressed to 30 psi. Okay, so this one 30 psi absolute. So you will see now if you're going to plot that one. So actually so kung mataas naman yung P2, so it will be on this side at P2. So since it is a lower side at P1, so it's one way of correcting our solution. Is correct or not. So if hindi naman na-indicate sa problem, initially, where this is your P1, so if you can refer to the PB diagram, mapapansin mo which is what will be the lower pressure usually, it will be the amount, the value we have that have a lower value. Okay. So, so we'll be solving now, which is we're looking now what is the work. We're looking for the work. So what will be the polytropic work? Okay. So we have the equation. So since we have the velocity given here in the problem, so we cannot directly solve it by means of applying the equation. So we have the change in velocity. Now, if we're going to isolate the system, for example, this one, okay. So if we're going to try to isolate this one, so if this is our suction, this is our discharge, and this is our suction, okay. Now, since we have the change in velocity from this is your point 1, so for example, um, this is our point 2 this side, and this is our point 1, okay, at this side. Now, so this piston now is connected to connecting rod. So for example, I'm gonna draw here a connecting rod. So we have here a connecting rod rotating. Okay. So in order to produce a reciprocating motion. Now, if we're going to isolate the system here, So we'll try to isolate this one. So I'm gonna mark this one as our isolation size line. Okay, I'm going to isolate this system in order to determine so what are the work that is being supplied and what would be the kinetic energy if there is, and also to determine what are the energy input and what is the energy that is being going out of the system. Now, in here, the intake stroke, so we're going to supply your uh, potential energy 1 plus your kinetic energy 1 plus your internal energy 1 plus your workflow 1. Okay. Now, on the other side, so we have your P2 going out here, your PE2 plus your kinetic energy 2 plus your internal energy 2 plus the workflow 2, which is going out. Now, so we're going to supply the work on the system. Then on the pins, so usually we have uh tawag dito, air fin in order to cool the wall of the cylinder. So air fin usually is like ganyan. So yun ang tinatawag na air fin. So you will notice this one also sa mga motorcycle, no? So there is an air fin or cooling fin. This is used for heat transfer sa wall. So in order to cool the cylinder wall, or it can be by means of a jacketed water. So which is since it does not produce too much heat compared to an internal combustion engine, so that's why it is using only an air fin like this one. So now those air fin rejected heat. So since you supply the work, you have a rejection of heat going out to the system. So we put here your Q. Now if we're going to do steady flow energy equation, your energy in is equal to energy out. Okay, so we have energy in, which is equal to your work plus the potential energy 1 plus your kinetic energy 1 plus your internal energy 1 plus your workflow 1. So okay. Then that is equate to your heat. Okay, so that is being rejected to the system plus your potential energy 2 plus your kinetic energy 2 plus your internal energy 2 plus your workflow 2. Okay. So remembering that our sign convention, so since we are supplying the work to the system, so the sign convention of the work and heat, it will be negative. Okay. So let's do arranging the equation. So we have now your negative Q minus your work is equal to the change in potential energy plus your change in kinetic energy plus the change in internal energy plus the change in your workflow. Since we have little I call this change in elevation from point 1 to point 2, so the change in elevation is 0, so the potential energy is 0. So this is will be cancelled out. So I'm gonna cancel now our potential energy. So what is left now is your kinetic energy. So we have the change in velocity. Since our kinetic energy is expressed in 1/2 times the mass flow rate, okay, so that will be times your velocity, that is raised to square. So we have the change in velocity from point 1 to point 2. So you will notice that the given, so we have the 35 feet per second for the velocity at the suction stroke, and for the discharge, we have the velocity of 170 feet per second for the discharge stroke. So it will not be zero out. Then we all know that our change in enthalpy and your workflow, okay, so it can be expressed as the change in change in internal energy can be expressed plus the change in workflow can be expressed as your change in enthalpy. So we can express our equation as your Q minus your work is equal now to your change in kinetic energy plus the change in enthalpy. We can further expand our equation, no? So we have 1/2 change in kinetic energy, 1/2 change in velocity, so that will be the mass flow rate, okay, times the velocity 2 square minus your velocity 1 square plus the value of your change in enthalpy, so it can be expressed as MCP. So that will be mass flow rate times your specific heat at constant pressure, then multiply it by T2 minus your T1. Now our heat also can be expressed as so let's transpose this one to another side. We can express our heat, or let's say our work now is equal now to 1/2 times the mass flow rate times your velocity 2 squared minus your velocity 1 squared plus your mass flow rate times your specific at the constant pressure. Then we have your T2 minus your T1. So this will be, since we're going to transfer this one, so it will be now plus on the other side. So we have the equation for the heat, the mass flow rate times your Cn times your T2 minus your T1. So that is your heat rejected is equal to M mass flow rate times Cn times your change in temperature. Now reviewing our equation here. So you will notice we don't have the mass flow rate. We have this one. B to B1 already given. So constant specific heat. Well, we can get that value for the specific heat, Cp. And for the, so we have the Cn, we don't have the value, and also for the T2. So let's try to solve the mass flow rate first. So from our PBM ideal gas law or equation, we have your P1, B1, which is equal to your mass flow rate times your R, and we have your T1. So we can rewrite our equation to get the mass flow rate. So we have your P1, B1 divided by your R times your T1. I divided by your T1. So our P1 given in the problem, so we have 14.7 psi. Okay, so that will be 14.7. So that will be psi. Okay, or we can express our psi in terms of pound force per square inch. So pound force per square inch. Then we're gonna multiply this one with the B1. So our B1 is given in the problem. So that will be the volume flow rate. So B1 300 cubic feet per minute. So this is 300 cubic feet per minute. Okay. So we need to do some cancellation conversion here. So pound force per square inch. So I'm gonna convert the cubic feet. So 1 feet, okay, is equal to 12 inches. So I'm gonna raise to this one to cube to in order to make it cubic. Then I'm gonna divide the whole equation by our R of the air. So that will be 53.34. So 53.34. Okay. Now for the 53 for the R of the air, we have 53.34. So the unit will be foot-pound force, okay, per pound mass degree Rankine. Then we're going to multiply our T1. Our T1 given to the problem is 540 degree Rankine. Okay. So let's cancel what is common on the cancel the common units. So we have pound force will be cancelled out. Okay. So inch, we have cubic feet, cubic inch. Okay, so this will be cancelled out also. So what is left is inch already. Then also we have your Rankine cancelled out. Okay. Then we have now your mass flow rate is equal to. Okay, so I forgot here. So since we still be needing the feet in order to cancel the feet below. So I'm gonna change this one to I'm going to change this square feet. So I'm going to use the square so that we can convert the square feet. So I'm gonna cancel this one so that we'll be in the same units now. So that will be square inch. So it will be cancelled out. Okay. So what is left? So it's already feet na lang may iwan. And we can cancel out the feet doon sa ilalim and below. Okay, we cancel out. Then what is left is pound mass per minute now. So we have the mass flow rate that is equal now to 22.05. 22.05. So that will be our pound mass per minute. So that will be the value for our mass flow rate. Now for our T2, temperature 2, so we have from our PBT relationship, so our T2 now is equal to your T1. So that will be the ratio of P2 over P1, then raised to the power of your N minus 1 over N. So we have now your T1 that is 540 degree Rankine. Then divided by your 30 psi absolute divided by multiplied by 30 psi the ratio, sorry. That would be 14.7 psi absolute. So that is raised to the value of 1.32 minus 1 divided by 1.32. So we have now the value of your T2 is equal to, so we have the value of 641.9. So this will be degree runtime. Now let's solve for the value of your Cn. So our Cn is equal to Cv, then multiply by K minus N divided by 1 minus N. So for the specific heat at a constant volume of air, so that will be equal to 0.1714. So 0.1714. So this is will be BTU, pound mass, degree runtime. Okay, then multiply by the value of the K, which is 1.4 for the air, minus 1, divided by 1 minus the value of N, which is, oh sorry, this is 1.32, minus 1 minus 1.32. Okay, so the value of our Cn now is equal to negative 0.0429. So that will be BTU, pound mass, degree runtime. Okay, so let's try to substitute the computed values here. So we have your work is equal now to 1/2 times the mass flow rate, which is 22.05. So that will be pound mass per minute. Then it will be multiplied to the velocity. So it will be 1/2 times the velocity squared. So we have 170 feet per minute. Okay, which is square. Just this one. So this is square minus we have 35 feet per minute. This is also a square. Okay. Then we're gonna add plus 22.05. So this will be pound mass per minute also. Then multiply by the Cp of the air, which is 0.24. So with the unit of foot pound force per pound mass degree runtime. Okay. Then multiply it by the change in temperature. So we have your T2 641 0.9 degree Rankine minus 540 degree Rankine. Okay. Then we're gonna plus here again 22.05. That will be pound mass flow rate per minute. Then we're gonna multiply the change in temperature. Oh, sorry, we need to multiply the Cn. So the value of the Cn, that will be negative 0.0429. So the unit we have here before, I think we use BTU. So it is BTU, pound mass, degree Rankine. Then we have 600, change in temperature 641.9 degree Rankine minus 540 degrees Rankine. Okay. So let's close the two parentheses. So we have now your work is equal to, now for this one, so we have the value of 1,488, 375, 0.375. That will be, so it will be foot pounds. So it will be foot pound mass. Sorry, it will be foot pound force per minute. Okay. Okay, so before we proceed, no, this I just like to add for this on our equation. So we forgot to add the conversion here. So since we are in the pound force, so usually we need to convert this one. So pound mass into pound force. So we need to divide the system, or this one, your kinetic energy. So for this one, we're going to divide by 32.174 for your conversion of pound mass, foot pound mass into pound force, converted to pound force. Okay. Okay. So what I'm going to do here, class, is um I'm going to divide the system. So I'm going to bring down this one. Okay. So I'm gonna bring down this one. So this is will be equal to, again, it will be 1. Para ng value nito, this is 1. Multiply by 1. Then divide by 2. Then I'm going to multiply the 32.174 for the conversion to that one, proportionality constant. So the unit here is pound mass, foot pound mass, no? Then it is ratio of pound force second squared. Okay. Then I'm going to convert that one. So the final result of this um, solution will be in the unit of pound force. So this will be in the unit of pound force, no, per minute. Now, since we're dealing in the heat, so I'm going to convert this one into BTU per minute. So we have the conversion. After I'm going to multiply this one into um, 1 BTU, okay, per minute. So that is over 778. So this will be put pound force per minute. So that's why I'm going to convert it into, I'm going to change this one in order for us to convert it into BTU per minute. So in terms of heat, okay? Then I shall continue my solution from here. So I'm going to add the 22.5 0.054 hour mm, for our MCP delta T, and I'm gonna add the MCN delta the MCN delta T also. So I'm just going to remove this one. Okay, so we're good to go. So let's try to solve the problem here. So by using your calculator now, so we have the value of your work. So that will be negative value sign here. So we have the value of um. So this will be our equal to 12.2. This is 12.2. So we are in the units of BTU now. BTU per minute. Okay. Then so in here we're going to cancel now. I'm going to show you the cancellation of our units here. So pound mass will be cancelled out. So this will be feet squared and minutes squared. Okay. Then so pound force. Oh, sorry. This is the units of our velocity here is seconds. So I'm going to change this one. Sorry for this one. Um, so I'm gonna change this one to seconds. Okay. Then cancel out our common units here. So our pound force will also be cancelled out. So this one will be cancelled out. And what is left going to left will be pound force. So this will be cancelled out by minutes din dito. Then for the conversion, second squared will be cancelled out also, second squared. Okay. Then our fifth, this one also will be cancelled out. So we have now what is left, it is the units of BTU per minute. Okay. So let's calculate also this one, yung MCP delta T. We have the value of 539. So this is 539.3. So that will be BTU per minute for units there. So I'm going to cancel there. Okay. So let's try to cancel the units dito. So pound mass, pound mass. We have your run kind. So we have for pound force per minute. Okay, so I forgot this one. We have the units for this one. This is, I'm going to change this one into, sorry for this one. This is BTU. So I'm going to correct this one. This is BTU. So that will be BTU pound mass degree runtime. Okay. So what we have left is BTU per minute now. Okay. So that will be 539. Then we have next is the work by the NCN delta T. Okay. So we have the value that we plus the value of MCN that will be um entering this value. So this is already negative. So we have negative sign here. So it will be negative 96.4. So this is will be also BTU per minute. Okay, so let's transfer the negative sign here on the other side. So we have 539. Sorry, this will be positive 96.4. Then to be BTU per minute. Then minus 539.3. That will be BTU per minute. Minus we have 12.2. So that will be BTU per minute. Finally, we have the work value is equal to. Okay, so remembering, okay, so I want to check this one. So we have wrong sign conventions here. I forgot to notice this one. So that's why our solutions are not in the correct path. So this one, since we transfer it to the going back to this one, so transfer into the other side. So this will become positive value. So you have here Q, okay, this one, okay. So this positive. So when you're going to transfer that one on the other side, so the value of our heat uh, is your MCN, no? Okay, it will be a negative value. So CP, so I'm gonna change this one into a negative value. So this is negative. Okay. Okay, so going back to our previous solutions here, is that this one. So our our Q, so this will be from the previous, so this will be the sign, it will be negative. So this is negative MCN, okay, it will be plus, and this is the value of negative already. Correcting that one. So we have the value of MCN. So when we going to substitute this one, so this one will become positive. Okay, substituting that one will be negative positive 96.4. Now transferring the negative sign from the word, so we have here. So it will be now negative 96.4. So when you transfer inside, it will be positive. Then from here, our negative sign will be transferred the other side. So it will be uh, negative sign. So we have now the value of 647. This will be 0.9. So the unit will be BTU per minute. Okay. Now, if we're going to change it to a horsepower, so since we would like everybody would like to know what will be the horsepower requirement for this system of a compressor, so we can convert that one. Okay, so we have the conversion of horsepower in British, so that will be 42.4. So 1 horsepower to BTU per minute is 42.41. Okay, I'm gonna write this one here. So that will be 1 horse. We're going to multiply it by 1 conversion. So 1 horsepower, that will be 42.41. So this will be your BTU per minute. So cancel natin yung common units here. So we have now how much horsepower requirement. So we have the value of negative, okay, negative 15.28. So that will be the horsepower requirement of the system. So take note, that is negative sign So in our thermodynamic cycle, it means that the work is being supplied to the system and heat is being produced going out of the system. Okay. So let's take a quick overview of the solution of the problem. Okay. So starting from here, okay. So we start the solutions from here. So okay, for the sample problem for this one. Okay, so now start from here, then continuing the equation on this side. Okay, so going down here. So for the isothermal compressions, and so this is one our solution. So okay, so you can follow that one. Then going down here.